Okay, so continuing with section 7.3, let's consider the following. So let's see, x and y coordinate axes. X and y, 2, 3, 4, 5, 6, 7, 1, 2, 1, 2, 3, 4, 6, 1, 2, 3, 4, 5. Okay, so I'm going to look at this in two different ways. So let's say we have vector u. So vector u, let's have it be 2, 3. And vector v, let's have it be 1, -1. Okay, so in standard position, this is vector v. And over 2, up 3, this is vector u. Okay, so let's consider something. Let's consider the case where I place vector v starting here. So it would be to the right 1, down 1. And let's consider what results here. Let's call this vector w. So do you agree that vector w has gone to the right 1, 2, 3, and up 2 from the origin? Okay, so now let's do the same thing. Let's do vector u over here. To the right 2, up 3. And vector v down here, over 1, down 1. But now let's consider this vector here. Let's call it vector t. So t looks like it goes to the right 1 from its initial point and up 4 to its terminal point. Okay, so let's see what happens with vector w. We know that it's 3, 2. But I claim that that 3 can be written as, oh my goodness, kitty, 1 plus 2, comma, and that 2 I claim can be written as -1 plus 3. So breaking this up, I claim that this can be written as 1, -1 plus, actually maybe I should draw that in purple, plus 2, 3, which of course is vector v plus vector w. Sorry, vector u. So that's kind of interesting. Now let's go over to this vector t. See if we can do the same type of analysis. So we get that t is 1, 4. So I claim that I can rewrite 1. Well, 1 is what? It's 2 minus 3, right? So I claim that, sorry, 2 minus 1. 2 minus 1, comma. I claim that 4 can be written as 3 minus a -1, or plus 1. So 3 minus -1. So that is, I can rewrite this as 2, 3, from which I'm subtracting 1, -1. So this is what? this is vector u minus vector v. Okay, so u minus v. Notice how the arrow points. It's pointing to u. So its terminal point is u, and it's coming from v. So that's how I do u minus v. So let's note. So note. So graphically, how do we add and subtract vectors? So graphically, number one, so vector addition is what we call tip to tail. So here's the tip of u and the tail of v. So we call that tip to tail. Tip to tail. That's how you add vectors graphically. And vector subtraction. Is tail to tail. Do you agree both the tail of u and the tail of v are coincident? So it's tail to tail. Okay, so let's consider. Let's have vector u be 2, 2. And say vector v be 3, -1. I don't know if I have enough there. Actually, let me undo that. Delete. Just draw a new one. It's the x and y coordinate axes. So x and y. Let's do 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so we'll copy and paste this. Okay, so I'm going to plot u, which is 2, 2. So here's u, and v, which is 3, -1. Then I'm going to complete the parallelogram. So I'm going to put v, which is 3, -1 over here. Oh, do you know what? I'll just go ahead and... Yeah, I guess I'll use the same color. So 3, -1 to the right, 3 down 1. This is also v. And let's have u be over here, which is up 2. So this is also u. Okay, so I've created a parallelogram with these vectors. And now let's look at the diagonal of the parallelogram. Oops. So the diagonal. So let's call the diagonal w. So w in this case is over 1, 2, 3, 4, 5, and up 1. Okay, so now let's go ahead and do the same thing over here. So we've got u is to the right 2, up 2. This is u. Vector v is to the right 3, down 1. This is v, but I'm going to once again do v from the tip of u to the right 3, down 1. This is also vector v. And u finalized right here, u, there we are. So we've got our parallelogram, but this time I'm going to look at the alternate diagonal, pointing to u. Call that t. So according to this, t goes to the left 1 and up 3 from its initial point to its terminal point. Okay, so let's look at W. So W is 5, comma 1. So I claim that 5 can be thought of as 2 plus 3. And I claim that 1 can be thought of as 2 plus a negative 1. That is, I can write this as 2 comma 2 plus 3 comma negative 1. Or, of course, W is vector U plus vector V. Okay. Now vector T, which went to the left 1 and up 3, well, I claim that negative 1, of course, can be written as 2 minus 3. And I claim that 3 can be written as 2 minus a negative 1. So that is, I can write T as 2 comma 2 minus 3 comma negative 1, otherwise known as vector U minus vector V. Okay, so how is this any different from what I've done? So this is called the parallelogram method of vector addition. So note, so the parallelogram, oh boy, spelling, parallelogram, there's no spell check here, parallelogram method of number 1, vector addition, is the main diagonal, right? So if I have my 2 vectors with the tails at 0, 0, as in the case of the left-hand side here with W, all the tails for U, V, and W are at 0, 0, so that's the main diagonal. So vector addition is the main diagonal. And of course, vector subtraction is the alternate diagonal, as in T. So vector subtraction is the alternate diagonal. As we see for T. And remember, if it's U minus V, I point to U. So we have to be careful there. You always, the terminal point is at U if it's U minus V. Okay. So maybe I should note that before going on. It's going to weigh on my conscience, so note. The terminal point of U minus V points to, well, it's the terminal point of U, right? The terminal point of U. So U minus V points to U. Okay, so now we have vector operations. So that'll be in purple. So vector operations. Like addition, subtraction, multiplication, and division. So let's let vector u be a comma b, and vector v be c comma d. And let's have k be some constant, some real number. So then we have the following vector operations. So number 1, so u plus v is the same as, or actually no, let me do it this way first. It's going to be a plus c, pardon me, comma b plus d. That is, I can add vectors component-wise, much like I do with points or coordinates. Okay, so number 2, u minus v. Of course, I can also do component-wise subtraction. So that's going to be a minus c, comma b minus d. And last but not least, the third operation is scalar multiplication. So if I have any constant k times the vector u, I can push that constant inside the vector. So this will be k times the first component, a, comma k times the second component, b. But we have to note something. So note if k is greater than 0, this implies that k times u is in the same direction as vector u. However, if k is less than 0 or negative, this implies that k times u is in the opposite direction. Opposite direction of u. Okay, let's also consider let's say we have u is any vector a comma b. Well, we know that this implies that the magnitude or length of vector u is the square root of a squared plus b squared. That's the Pythagorean theorem. Radius. Let's say now we have k times vector u. Well, according to the above, that's k times component a, comma k times component b. So how does this change the magnitude? Well, now the magnitude of k times vector u is going to be the square root of now k squared a squared plus k squared b squared, which means I can factor out k. So this is k times the square root of a squared plus b squared, which is just k times the magnitude of vector u. So what does that mean? That is, i.e., k times vector u has magnitude slash length k times that of vector u. So when you multiply a vector by any number, it makes its length that many times greater. So for example, so let's let vector u be 2 comma 1 and vector v be 3 comma 0. So plot the following. Okay, so number 1, let's plot u plus v. Okay, let's have u be blue. So u plus, let's have vector v be yellow. U plus v is going to be 2 comma 1 plus 3 comma 0. So that's going to be 2 plus 3 comma 1 plus 0. Okay, so that turns out to be 5 comma 1. Okay, so let's plot those. So x and y coordinate axes. X and y. 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 3. 1, 2. Okay, so we know we have u is 2 comma 1. And we know that v is 5 comma, sorry, no, v is 3 comma 0. That's just to the right, 3. And I claim that the sum is over to the right 5, up 1. Does that look like the diagonal? U plus v. Well, yeah, if I were to create this. Yep, it is a diagonal. So let me actually go ahead and put that. So u and v. Yeah, check mark. Okay. So it is the main diagonal, so we're set. Make sure this is 5, 3, 1. Okay. 1, 2, there. Okay, so number 2. Let's plot, what shall we do? Let's do negative 3 times vector u. Okay, so now we have a negative 3 times vector u, which is going to be a negative 3 times a vector, 2 comma 1, which is going to be a negative 3 times 2, comma, a negative 3 times 1. Okay, so what does that give us? That gives us a negative 6 and a negative 3. So let's go ahead and plot that. So x and y coordinate axes. So x and y. 1, 2, 3, 4. 1, 2, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6. So this is negative 6. This is negative 3. This is 3. This is 2, 1. Okay, so here's vector u. Vector u is 2, 1. That's vector u. But now let's look at negative 3 times vector u, and that's negative 6, negative 3. So this is negative 3 times vector u, and it's in the exact opposite direction, and it's 3 times longer. Okay, so 180-degree difference. Let's see if I have enough room to do another one. Let's do number 3. Let's do vector v minus vector u now. So vector v minus vector u, wrong color, vector v was yellow. So the point should be pointing, the terminal point should point towards v, right? So v minus u. Actually, maybe I should do this in a different color. Let's do it in pink. I've already used purple. V minus u is equal to, so I have vector v is 3, 0, 3, 0, and I'm subtracting from that vector u, which is 2, 1. So I get 3 minus 2 and 0 minus 1. So 3, 0, 3 minus 2, 0 minus 1. So that gives me the vector 1, negative 1. Okay, so let's see. X and Y coordinate axes. Okay, so we have vector v to the right 3. And we have vector u. Actually, let me put that v beneath. Actually, I want to do something in particular, so let me put v over here. And vector u, of course, is going to be 2, 1 over here. So supposedly, I'm going to point towards vector v. So is this the same as 1, negative 1? Yes, it is. So this is indeed vector v minus vector u, because I'm pointing towards vector v. So that works. Okay, so before I go on to the next subsection, I think I'll stop this here.